What's today's topic, Kevin?
Today's topic is on hybridization.
Okay. Why do we want to talk about hybridization?
Um, I think when you learn like the energy level diagrams and electron configuration, sometimes there's a disconnect between that and Vesper theory and how atoms make bonds and the shapes that molecules make. So I think hybridization is kind of a good transition or a good segue between both of them.
Okay. All right. So I have a couple of ideas on this one. Um, One of the things we know is that methane, CH4, well, let me show you the photoelectron spectroscopy uh, spectrum for methane, and you tell me what you see.
All right.
What do you see there, Kevin?
So right now, I see the horizontal axis is the number of electrons. The vertical axis is energy in some hundreds, and then I see two kind of major peaks or triangles.
Right, right. So just like we had with all of the photo electron spectroscopy for individual atoms, you can do the same thing with a molecule. You take the molecule, subject it to light, and you can drive off electrons. And so if you look at this graph, these two electrons down here are the 1s electrons in the carbon in the methane. Those are the interior electrons. And that actually corresponds to 2 electrons. But if we look up here at the top, there's one big peak with this little shoulder on it. And that is 8 electrons in carbon, in methane, that are basically all the same. So if we think about the energy level diagram for carbon, 1s, 2 electrons in the 1s, 2 electrons in the 2s, and 2 electrons in the 2p, somehow we go from having some electrons in the 2s and some in the 2p to having 8 electrons that are all essentially the same. And so we have to have some way of thinking about what's going on with the electrons in the orbitals such that you can have 8 electrons that are identical in a methane molecule.
Yeah, I was just going to add on to that. Because if you have some in the 2s and some in the 2p, then you would want to have maybe 3 different peaks, just like when we did carbon in the original photoelectron spectroscopy graph.
Right, right. And so in methane, there's clearly something going on that all 4 of the carbon-hydrogen bonds, 4 bonds, 2 electrons each, giving us a total of 8 electrons. There's something going on that says these bonds are all the same. They're not different from each other. And so that's one reason why we should start to believe in hybridization of orbitals. So that's what we're going to try to explain. Okay. If we look at this middle row here in this graph, there are 4 orbitals made from hybridizing, which is another way of saying combining 3 different p orbitals and 1 s orbital. And if we do that, we get the tetrahedral shape that we've seen with methane, and we are able to rationalize how we could have 4 equivalent bonds surrounding that carbon. And so that's why we would say something like something like a methane molecule with a carbon in the center here and 4 hydrogens at the ends of each one of these bonds would have a tetrahedral shape.
And so when all the different orbitals combine, so with the tetrahedral example, the S plus P plus P plus P, all of those are equal energy level.
Correct, correct. And so that's why, and if we put 2 electrons in each one of those, we can end up with 8 electrons as all having the same amount of energy, so that when we do the photoelectron spectroscopy experiment on methane, we can end up with this peak of 8 electrons. Okay?
All right.
So if we can begin to accept that, then we look at some other molecules like boron trihydride, and it has 3 hydrogens surrounding a boron. And we can understand that by saying, if we combine 1 s orbital with 2 p orbitals, we can get a shape that allows us to have a hydrogen at the end of each one of these lobes in the molecule. And so we would have a trigonal planar molecule when the hybridization involves 1 s orbital and 2 p orbitals. Okay. Now, we also know that there are some other molecules that have weird formulas, right? That make don't make any sense to us. For instance, there's SF4. That's sulfur with 4 hydrogens around it. Well, it also has a lone pair, so it's a sulfur with 5 things around the outside. And the only way that we can make any sense of figuring out how to put 5 things around the outside of an atom is if we take 1 s orbital, 3 p's, and 1 d, we can come up with really a mathematical model that says the hybridization of those 1, 2, 3, 4, 5 orbitals, the s, 3 p's, and a d, 1, 2, 3, 4, 5 orbitals, allow us to have 5 sets of electrons around a central atom. And that shape, it's called trigonal bipyramidal, but it's a combination of an s, 3 p's, and a d that allow us to bond 5 pairs of electrons around a central atom.
I see. Okay.
Likewise, we know there are some molecules that have 6 things around them, like sulfur hexafluoride. Sulfur hexafluoride has 6 things, and so we need to have some way of thinking about how do we get 6 atoms bonded around a central atom. And if we take an S, 3 P's, and 2 D's, so S, P3, D2, we can end up with an octahedral shape where all of the bonds are 90 degrees from each other, and we can have 6 things around it. With Vesper theory and with these hybridizations, we're able to rationalize how we could possibly have 6 things surrounding a central atom.
Yeah, it's really confusing at first when you're trying to learn Vesper theory and even just bonding in general, but with enough practice and some understanding, this will hopefully make a lot more sense now that you've been exposed to hybridization.
Yeah. So the mathematics of this are way beyond the scope of this course. And there may have been a time in my career when I understood a little bit of the mathematics, how you combine these orbitals in this hybridization model. But if you recall waves and combining waves and constructive interference and destructive interference from maybe a physical science course when you're thinking about waves, the mathematics of this is similar to that, in that the way that we mathematically combine 1 s orbital with 3 p orbitals gives us the possibility of having this tetrahedral shape as a plausible idea. And the advantage of it is that it helps explain what we see experimentally. Experimentally, we've got a single peak in the methane, and so therefore all four of the single peak with 8 electrons. So therefore, all 4 of these bonds must be equivalent. And the only way we can get to those 4 bonds being equivalent is if we do a mathematical combination of an S with 3 P's. If you can begin to accept that, then maybe you can begin to accept that S with 3 P's and a D can give you 5 things bonded around a central atom, which we see experimentally. If you can begin to accept those 2, then maybe you can begin to accept that you can have 6 things bonded around a central atom. And mathematically, we can make sense of it if we're combining an S with 3 P's and 2 D's in a similar way to the way that we do, that you might have seen constructive interference and destructive interference of waves in some other course.
All right. I think that's all then.
Okay. Thank you. Thank you, Kevin.
Thank you, Dr. Hunter. Talk to you next time.